Hello everyone. Today we are going to do 11.4, the comparison test. The goal for this class is we want to compare our series with some known series, for example, P series, geometric series, and then tell our series converges or diverges. So the goal, we want to compare with series whose convergence is known, like P series. Do you still remember what is P series? Like this, right? And when P greater than 1 and less equal to 1, diverges, converges. And also geometric series, which is A R to the n, O n minus 1, doesn't matter, depends on n start from what, right? Something like this. And when R less than 1 converges to A 1 minus R, R greater equal to 1 diverges. So we want to compare with those series. Now let's take a look at the theorem 1. Comparison test. Okay, so here we have three series. Let series AN, CN, and BN with non-negative terms. Suppose that for some n, we have this information. AN is in between BN and CN. Okay. For all n greater equal to some. So that just means start from some n. They satisfy. This condition is satisfied. So if Cn converges, then series CAN converges. Second, if Bn diverges, then the series AN diverges. Okay, that's the conclusion. How to understand this comparison test? We can think this way. You can think about the partial sum AN and the partial sum like a capital C N is a partial sum for series Cn. And then because all the terms of AN is less than Cn, so definitely the partial sum should be less than the partial sum of Cn. And because Cn converges, so our AN has a finite limit. In this case, AN has to be converges. Okay, you can think this way. And if our series is greater than or diverges 1, same thing, diverges then like a Bn, and that means, and the Bn diverges means this is infinity, right? So An has to be greater than infinity. That means An has to go to infinity. So that's why An diverges. So just keep in mind, when it's smaller than converges, it's converges. Larger than diverges, it's diverges. Now, let's take a look at how to use the comparison test in our example. Example 1. Let's take a look at the first series. Here, I'm going to give you two example problems. The first one, 5 over 5n minus 1. from here is not p-series, is not geometric series, and we don't know, we have never seen this kind of series. It's not telescoping. So how to tell this converges or diverges? We want to compare by looking at this series. We want to compare this with 5 over 5n. Like we can ignore the number 1, and let's see how to compare them. Firstly, you can see 5n minus 1 and 5n. Who is larger? 5n minus 1 should be smaller than 5n, right? And then, because it's in denominator, 5 over 5n minus 1 should be larger than 5 over 5n. Opposite way. And this is 1 over n actually. And now we know the series 1 over n. What is the series 1 over n? We call it harmonic, right? Harmonic series. And this is also a special case of the p series. When p is 1, it's also p series with p equals 1. And we know that series diverges. And our series is greater than that diverges 1, so the series also diverges. Okay, this is how we use the divergence comparison test. Greater than diverges, diverges. Let's take a look at the second problem. Okay, the second one is not given by this sum notation. It's given by this one. Given by 1 plus 2 plus root 1, 4 plus root 2. So the general term is 2 to the n plus square root n. Okay, this one. And let's see what is the an. Firstly, let's write down an. This is our an. We want to compare, this an with some other series. And then right now in the denominator we have two terms. We don't know how to do this directly, right? But we want to compare with just one term. So here we have, we can compare with this, this thing. Okay, and firstly we have to know convergence or divergence of those two series, and this actually is geometric series, and with r equals 1/2, actually this converges. And 1 over root n, this is 1 over n to the 1/2 power. This is p series with p equals 1/2, which is less than 1. When p series, the p less than 1, we know that is diverges, right? And in the denominator of an, we notice that the two terms, we have two terms, and it's a sum of those two terms. If we want to get rid of one term, so let's see, 2n plus this thing should be less than or greater than something. And we know 2 to the n plus root n, the denominator is greater than something, so whole thing has to be smaller than something. So smaller than the convergence diverges, so we pick the convergence one, so which is this thing. Okay, so we don't pick the greater than the divergence because the denominator is greater than something, the whole thing has to be less than something. If less than, we pick the convergence. Can you understand why we pick 2 to the n, not the square root n? And this converges because this is geometric series, we know converges, then this also converges. Smaller than converges, right? Now let's take a look at the exercise problem. The first one. N over n to the fourth plus 3. The second one, cosine square n over n to the 3/2. Okay, two problems. You can try. Now I will give you the solution for the exercise problem. But you should pause here. Do those problems by yourself. Let's see. N over n to the fourth plus 3. We want to get rid of the 3, so it should be n to the fourth plus 3 greater than n to the fourth, so whole thing smaller than this. Is that correct? And simplify, this is 1 over n cubed. And we know this is a p-series. And the p equals 3. So this converges. P-series converges. Then our series converges. Because it's smaller than converges, it converges. Okay. Next one. Whenever we see cosine, do you still remember when we learn the sequence, we have a sandwich theorem. Whenever we have cosine or sine, we have this property. Cosine n is always in between 1 and the -1. And for our case, this is square, so it's much even easier. Cosine square n is always less than 1, right? It's positive actually, greater than 0, less than 1. So our series, this less equal to 1 over n to the 3/2. And also same thing, 1 over n to the 3/2 is a p-series with p equals 3/2. When p is 3/2, that is greater than 1. Can you tell this converges or diverges? Converges. Then our series smaller than a converges, so that is converges too. Convergent. Okay, that is convergent. All converges. That's the exercise for convergence, for the comparison test. So in this section, we are going to do two theorems. One theorem is called comparison test. The other test is called the limit comparison test. Let's take a look. It's called the limit comparison test. Okay. They are all comparison tests. Same thing. We have a non-negative term series. Suppose that an greater than 0, bn greater than 0 for all n greater or equal to n. And first, if the limit an over bn is a number c, then both series an and bn converge or diverge. Second, if the limit n goes to infinity, an over bn equals 0, then and bn converges, then an converges. I will show you what's the meaning of this one, okay, later. So if the limit of an over bn is infinity and bn diverges, then an diverges. Let's take a look at the three cases. The first one, an, bn, the limit equals c. That means they go to some limit at the same speed. So they both converge or diverge. They have the same property. The second one, if an over bn equals 0, okay, and the bn converges, that's bn goes to like a bn, the partial sum goes to a finite number, or you can say bn goes to 0, because for the convergence series, the bn, the nth term has to go to 0, right? And if an over bn goes to 0, that means an is smaller than bn. Okay, smaller than bn, then definitely smaller than converges, diverges. The next thing is an should be much larger than bn because the limit goes to infinity. That means an is greater than bn, and greater than diverges because bn diverges, greater than diverges is same as the first comparison test. So this is just another way to get of the comparison. Now let's take a look at the example and see how to use the limit comparison test. The first one, 2n plus 1 over n squared plus 2n plus 1. Okay, so this is a series like an, because we want to do limit comparison. We want to know who we are going to compare with, like a bn. What is the bn? So we need to create a series bn. By looking at this an, we usually, when n goes to infinity, we can ignore those numbers, because when n goes to infinity, 1 constant and the 2n plus 1 is much smaller to n squared. So we can just ignore those terms when n goes to infinity. So we like to compare with bn, which is 2n over n squared. So we can say this is just compare with 2 over n. Simplify. Okay, here we simplify. This is our bn. When we do the limit comparison test, we find a series we want to compare with. So let's do the limit. an over bn equals what? N squared plus 2n plus 1. This is an, right? And divide bn. We know bn is, let's see. And then we simplify. 2n plus 1 over n squared plus 2n plus 1 times n over 2. And simplify, let's see. On the top, times 2n plus 1 with n, 2n squared plus n. Bottom, 2n squared plus 4n plus 2. Right, just multiply them together. And now find the limit of this one. I think we learned this in sequence. What's the limit of this term? Coefficient of the highest power. So 2 over 2 should be 1. That's the limit. So in this case, you can see this belongs to which case? Number 1, 2, or 3. So an over bn, the limit is constant number c, right? So here is constant number c. So they both converge or diverge. And now let's take a look at our bn. Our bn is this series actually. This is what? Harmonic series. Or you can say p series with p equals 1. And we know this diverges. Then our series, you know, they have the same because this is number, so they both converge or diverge. So our AN should be converge. Okay, let's take a look at another one. Let's do the exercise. We can skip it, you know. This is pretty easy one. Okay, let's try to do them in the exercise problem. The first. Second. Learn by doing. So we try to do more exercise problem and then we will know this better, right? Number 3. And yeah, we can just do those 3. And then you can pause and then do the exercise and I will give you the solution. The solution for the first exercise, we choose our Bn to be n over n cubed, which is 1 over n squared, because we just ignore those terms. Okay, how to choose Bn. And now let's do the limit comparison. That means we use An over Bn over Bn, which is n minus 2 over multiplied by n squared. Simplify. And this becomes n cubed minus 2n squared. The limit goes to 1, so they both converge, diverge. But because this Bn, we should say Bn, or you can say this is a P-series converges, because that's P-series equals 2, okay, with P equal 2, converge, so our series converge. Next one, our Bn, we choose, let's see, ignore the number 1, so let's do the limit comparison. Simplify. So most of the time we just do the simplify, right? Now we cancel, we divide by both by 2 to the n because we want to simplify. So here 1 over 1 minus 1 over 2 to the n, and the limit goes, this goes to 0, so the limit of the whole thing goes to 1. So say same thing, they both converge, diverge. And because this is geometric series, converges, so our series converges. The next one, the last one, you can see we like to choose Bn to be root n over n, and we can simplify here. You can do any method to simplify. You can use power, change them into like a power function and then cancel the power, or you can do this way, but it's going to be 1 over root n after we simplify Bn. And then we do limit comparison, that means An over Bn, which is, and divide by Bn, times root n, simplify, combine multiple n and n becomes root n with root n become n, and this limit goes to 1. So that means A and Bn both converge, diverge, and because our Bn, so the very important is you have to know what is the series Bn, converges, diverges. What's the property of this series? And this is, can you see what is this series? That is P series with P equals 1/2 and less than 1. So the series Bn, we can say diverges, right? So our series, which is An, also diverges because they have the same property, both converge or diverge. So that's the exercise problem. You can see all the problems in this section, we have to find a known series to compare with. So how to find the known series to compare with? We just look at the series and then ignore some constant term, some lower power term, and find an easy series which is known, like a P series or geometric. Okay, so try more homework problems. You should be okay. Just 2 tests here. We can stop this section.